Okay, so today we're going to do two things. One is we'll continue with the most fun part of the class, that's drawing VM diagram. We'll go over quite a few examples. We'll go through examples to learn. All right. And the second part, we'll leave some time to actually talk about the problem from exam 1. All right. So we'll kind of give you the solution. I know some of you still don't know what's wrong. You know why I'm not getting the full credit, right? Which part was wrong? Okay. So let's first talk about the VM diagram. Okay. Just quickly, let's review what we learned from last time. We learned a way you can do the VM diagram without cutting and then write equation equilibrium, right? You can directly draw the VM diagram by following 7 rules that I put up here, right? So the first one is you always have the 0 point. Start with 0, end with 0. So always there are 4 points should be there. So for VM diagram, nobody should get the 0 on a problem, right? At least you should draw this 4 point there, right? All the 4 points there. Okay, then the second one is if you have a constant force, then the V will jump, the shear force will jump. So force make force jump. And similarly, movement only make movement jump, right? So that's when you draw it. If you see a constant movement, your force will be continually, gradually change. But your movement will jump because you see a constant movement. And vice versa. If you see a constant force, only the force, the shear diagram jump. All right. And then the maximum value of the moment is at where you find the shear stress is 0. Or you can say the minimum value also at where shear is supposed to be 0, right? Because m dx equals v. That's why. All right. Okay, then this one actually not used that much. It just say when you have a distributed load, right? If you see the arrows pointing downward, then your curve should be a concave, what do you call it? Concave down. So this way, right? So most of the problems we have will be all the distributed load pointing downward. So you should always have this curve this shape. So you never have this shape unless the Q changes the direction. So that's what this means. Right? And then practically we have this relation here. But when you draw it, actually we really use it. This one we use for you calculate some of the values, right? But we actually use this one a lot. So the area of the V, right, between 2 points, between point A and point B, equal to how much the M changed, right? The change in M is equal to the area of the V between these two locations, right? So you can actually put the limit there. I don't have it here. So you can put, say, from A to B, right? So V change from point A to point B equal to the integral of the Q from A to B. And then the M from A to B, the change equal to the V integral from A to B. All right. So then to summarize, you see the shape of the curve that's listed in this table. So if there's no distributed load, the V will be constant, and then M will be linear. And then if you have a constant Q, then V will be linear, and the M will be parabolic, right? Quadratic format. Okay. All right. So this is the one example we went through last time. So I won't go over it. I'll just move on. Okay. So we want to go over quite a few examples today. All right. So this is the first example. Okay. So we have this situation. Make it easier. Let's say we know all the values. So give L value. Okay, what's L? Give me a value. 10. Okay. L equals 10. Now what's A? Give a value. 2. Okay, so here equals 2 meter long. This 2 meter long. Okay, P value. 20. All right. Okay, so 20. That means this is also 20, right? So you have a pair of force P equal 20 applying in between, right? On what do you call this beam? Simple beam, right? This is a simple beam. So we should be able to learn how to draw VM diagram for simple beam, cantilever beam. Cantilever beam we had covered last time. Now simple beam. And then later on we're going to have an overhanging beam. So for all 3 type of beam, you should be able to draw the VM diagram. They're all determinants. You just can go ahead, find the reaction forces, and then draw the VM diagram. Okay, so step 0 again. What's the step 0? If you want, draw the VM diagram for this one. What's the step 0? Now we don't need the cut anymore, remember, right? Free body diagram, find out the reaction forces. That's the key step, right? So I call step 0, it's basically a very critical step. So always find the reaction force first. Then you can go ahead and draw it, okay? And most, actually I won't say most, but many mistakes come from this critical first step. If you don't have the statics, okay, so here you will show some weakness. So if you know how to draw the, write the equation of equilibrium, find the reaction forces, then you will be in very good shape for this part. Okay, so we need to find the reaction forces. All right, so you need a free body diagram. So here is a reaction, right? So you have RA, then here you have RB. That's a free body diagram, now complete. I use this one, right? Load is labeled there, reaction is labeled there. Okay, now can we find the RB? Okay, so what do you use? Sigma Fy equals 0, right? Okay, now translate it. Okay, so RA, oh, maybe I'll put it here. RA plus RB. All right. Minus P, then minus another P equals 0, right? Is that correct? Okay, so we know P, so therefore RA plus RB equals to 2P, and that is 40. Okay. Well, 2 unknowns, 1 equation. So we need 1 more equation. Moment. Okay, so moment to where? To A. Okay, so I say sigma MA equals 0. Now translate. Or write it straight out. Okay, so P times A. That's for this. So you're talking about moment to here. So the first one you say is this P. So P times A. That's P times 2, right? You can write P times A or P times 2. Either way will be fine. Positive or negative? You just define one. Which way you call positive? Clockwise or counterclockwise? Counter. Okay, so I think in static you label this way, right? Remind you that's the positive direction. Okay, so therefore you have negative P times A, P times 2. Okay, then you say this force. So you have negative P times, what's the length? L minus A, that's 8. Okay, so I can just jump a step, so it's 8. Okay, then I see this force, so I have this RB times L, right? 10. Okay, positive and negative? Positive, following my arrow direction. So positive, so plus equals 0. Okay, from here, what's RB? Okay, if you're not sure, let's write 1 more step. So this will be negative what? 10 times 2, so negative 20, right? This will be negative 160. Okay, then plus RB times 10 equals 0, right? Okay, so 0, 0, 0 cancel out. So I divide 10 to the whole thing. Now what's RB? 100? Someone say? So RB equals what?
Shouldn't the first P times A be 40? It's 20 times 2.
What's the P value? 20. Okay, so I have the first term P equals 20, right? Times 2. Okay, 40. Yes, thank you. I made a mistake here. So 40. Okay, thank you. So P equals what? RB equals what? Equals 20. Okay, so you are correct, right? I was wrong. Okay, RB equals 20. Now what's RA? You can take it back. You get it confirmed 20. Okay. Here's one suggestion. Because many times we are making mistake determining RA, RB. Okay. So before you move on, draw the VM diagram. Do another check. Okay. How to check it? You can check sigma M to point B, see if it's equal 0. Okay. Or you can use sigma MB equals 0, find out RA, and see if this two way you get the same RA. That's one way of checking. Or you just plug all RA, RB value in, see if sigma MB equals 0. Okay. So make sure you do this step as a check. Okay. If you get the wrong RA, RB, everything else done will be wrong. Right? So it's critical you get the RA, RB correct. That's why it's important. You just spend 1 more minute here, check the MB, see if it goes there. Okay, so we can check one way or the other. Which way you want to check it? Plug these values, right? Okay, let's say we know this one is 20 here. This one, we know it's 20. Now, can we check if sigma MB equals 0 or not? Yes, so RA times 20. So you have 20, first term, 20. We talk about to this point, right? So 20 times 10. That's RA. Then you have minus, actually we call this way positive, right? So this will be negative. Then plus 20 times 8. Then plus 20 times 2. Is this equal 0? Does it equal 0? Yes, then we're correct. Okay, so now we can move on, draw the VM diagram. All right, so the way I would recommend you do this way. Just draw this just underneath the picture. So you have the V here, then you draw the axis here, right? So this will be 10, right? And so then you have the M. Okay, so you draw, I kind of draw a dotted line. See here, this is location 10, right? So this will be the M diagram. Okay, now start 0 and 0, right? Row number 1. So immediately you have this 4 point. 1, 2, 3, 4 point correct. Right? You should always get this 4 point correct at least. Okay, now for the V. Okay. When you draw, when you start, okay, from this side, when you start moving, okay, what do you see first? First, you see the RA, right? Immediately you see a force, a constant force. Now remember rule number 2. When you see a constant force, we will jump, follow the arrow. So arrow pointing up, so I need to jump up. How much? 20. Okay, so it'll be up here. Now I see what? I see nothing, right? Q equals 0, so this will be constant. So Q is 0, constant. Now I see a constant force. Okay. Follow the arrow, right? Force follow force. So V will follow P. Okay, so you go down 20. Oh, back to 0 line. Now, do I see anything here when I move? No, nothing. So it'll be 0. Keep going 0. Now I see a force. Okay, point down, so I go down. 20, right? Then nothing. So now I see another force, go up. So you go from start 0, and then eventually end at 0. Okay. Any questions about this one? This is easy, right? Okay. Now, what about M? Okay. When you start, what do you see first? Constant force, right? RA there. Okay. Does the moment jump when you see a force? Yes? Remember, force make force jump. Moment make moment jump. If you see no movement, moment don't jump. So there should be no jump. So you go either this way or this way, right? No jump, you just gradually changing. So you go up or go down. Okay, we go up or go down? Why up? Well, I heard someone say down. Okay, let's say from this point A here to this point B here. How much the moment change? Is this area, right? Area on V. Okay, so it's this area. This is a positive area, negative area. Positive. V is positive. It's up. So positive area. Okay, how much is this area? 40, right? 20 high, 2 long. Okay, so 40. So therefore, from point A to point B here, I should jump up 40. So this will be from 0 to 40. Because I start from 0. So therefore, the value here will be 40. Right? moment change is the V area. So that's 40. Okay, now from here, what I say? Y constant. There's no accumulated area. If you move to here, from point B to point C, how much area you accumulate? 0. So therefore, V doesn't change. Same, you keep going, no change. Right? Okay, now once here, you see something here, right? At this point, let's call this point D. Okay, now you see some V. So movement going to change. Okay, from this point D to point, let's call point E. Okay, how much the movement change? It should supposed to be this area. Now, how much is this area? Negative 40. So you go down by 40. So from 40, start going down 40, so you're back to 0. Right? So you start 0, end 0. Well, that's perfect. All right.
When you say jump, what do you mean? Are you saying like
I see if you have
jump or
the force will jump, the shear force will jump if you say a constant force. Right? The moment diagram will jump if you say a constant movement. And here we only have constant force, so only the V diagram there will be jump. Okay, we'll have another example with the movement that you see. Okay. All right, any questions here? No? All right, so this looks easy, right? So there will be homework for you to practice on. Okay, here just quickly, very simple concept here. Okay, this situation here, when you have a pair of force that is equal applying on beam, okay, this one we call a 4-point bending experiment. We actually use this a lot to test materials to find their property. Okay, the reason is, if you look at this part, the middle portion from point B to point D, there is only bending moment, right? There's no shear. Okay, only movement, only bending, no shear. So therefore, we call it pure bending. Because only bending, no shear, right? So we call pure bending, right? So this experiment actually used a lot in the material lab. If you go to the do the test, you know, people use this for a bar. They want to find out the property, use 4-point bending, and that's it. All right. Okay. Any other questions? Okay, let's see if we have a movement one with movement. Let me see if I want to jump a little bit so we can have an example with a movement. Okay, here, this one. Okay, any questions? No? All right, let's look at this another example. Here, again, a simple beam, right? Okay. Is this complex enough, or you want to add something to it? How about we add another force to it? You like to add the force or do this one? Add the force?
Yeah.
Okay, let's add the force here. Okay, a load P here. All right, say we know the load, right? So we know the value. Let's give a value. 20 again. All right, 20. Okay, length, we'll give 10 again, right? That's okay. All right, so this A, we'll say where you want this A. Maybe 1/3, look like 1/3, right? Or 10 1/3 is hard to give. So you want to put maybe 6?
21.
Which one is 21?
The length is 21.
The length is 21? Okay, make it 21, so you have 1/3, right? Okay, 21. So this will be 14. Then this one will be 7 here, right? Okay, MO, we need to give a value. Equals 1? That's too small. Give something in the V. How about 5? Okay, let's try 5. I don't know what will come out, but we'll just... Okay. All right, so this one... Okay, again, same. We just want to draw the VM diagram. Now, step 0. Free body diagram, you find the reaction. And this one actually pretty standard. You know RA and RB. Okay. In this case, it's not symmetric anymore. So RA and RB should have different values, right? Okay, now write the equation of equilibrium. Find the RA, RB. What's the first equation? Sigma Fy equals 0, right? Okay, so what do you have? Ra plus Rb, what? Minus P, right? So minus the 20, and that is the P value. Then minus 5 equals 0. What I got wrong here? You cannot minus the moment to a force, right? They're a totally different thing, all right? So basically, this will equal 0. Okay, so Ra plus Rb will be 20, so we know that. Okay, now, next equation. Sum of moment to where? A, okay. So summation of moment to point A equals 0. Okay, translate. To point A, remember it's 2.8. So what do you have? P times the 7, right? That's positive or negative? Negative. Okay, then what else? Plus the MO, that's the 5, right? What else? Plus RB times 21 equals 0. All right? Okay, so from this one, can we find out RB? So this will be negative 7, so that's 140, right? Then plus 5. Oh, that's too small to cancel anything. All right, then plus RB times 21 equals 0. Okay, so what's RB? That's weird number. Okay, can we somehow make it the integral? Can we change MO? Change MO to what? Can make RB integral? 21 times, let's say 21 times 5 is what? 105. Okay, how can we change from 140 to 105? 35, right? So we can make this one 35. How about that? Oh, 35 instead of 5. Okay, so this way, this will be, if you plus 35, this will be negative 105. So therefore, that gives you RB equals what? 5. Okay, RB equals 5. Now can we find RA? Okay, what's RA? RA 15, right? Okay, is this correct? Check, right? So write sigma MB equals 0. Okay, check if it's correct. Is it correct? To point B, right? To point B, so you have 15 times 21. That's going this way, so negative. Then you have the 20 times the 14. And then you have this 35. Is this equal 0? Anyone got a calculator? I think it's 0, right? Okay, so that means we got RB correct. Okay, now we can move on. Let's draw the VM diagram. Okay, so I will make it here, the V. Okay, then here's the M. Okay, so this end here, and then this start here, and then this line is here. Okay, now let's do the V. When you start, what do you see?
0.
I see 0. I see RA. Oh, okay, start 0, right? That's 4.0, 0, 0, 0. So you are correct. 0. Okay, but once you start 0, immediately what do you see? You see RA, right? So RA equals to 15. So I need to jump which way? Up 15. So here's 15. Then I say nothing, right? So you just go Okay, here I see 20. Okay, what's the move? Down 20. Okay, so here will be -5. Okay, now you see nothing. So constant. Oh, I see a movement. Should I jump? No, because that's movement. Okay, remember movement. So force see a movement. Ignore it. So just keep going. 5 here, then go back up to 0. Say RB is 5. Right? Okay. V is done. Now what about M? M start 0. Immediately you see no constant movement, so now jump. You just gradually start. Okay, immediately you see this area accumulate. So if you move to here, you accumulate this much area. If you move this whole way from point A to point B, you accumulate this whole area there. Okay, how much area you accumulate from point A to point B? Will be 15 times 7, right? 15 times 7. Okay, what's that? 105, right? Okay, 105. So we 105. So 0 go to 105. So here's 105. All right. Now cross this point. I start accumulating negative area here. So I know it will go down. Right? But go down by how much? So we know from this point to here, for example, if you look at here, the whole thing here, 5 times 14. This whole area is how much? 5 times 14. 70. So you should go down 70, right? If you say you go down 70, go this way. But this is this correct? No, because before you reach there, when you move here, right? You will see something here. So therefore, see something here. So therefore, you cannot continue. You just first go from here to here. So you have to calculate this area first. Okay, this will be 5 times 7. 35, right? So therefore, from 105, you need to go down 35. So where are you located? 70. Okay, so this point is supposed to be 70. Okay, once at 70, what do you see? You see a counter movement. Okay, a movement pointing this way. Okay, now should the movement jump? When you see a counter movement, so the M will jump. Okay, now jump which way? How much? You jump by 35, right? Okay, but now up or down? Up or down? You remember that diagram we show? When you have this M going this way, you jump which way? Remember that cartoon we show? Okay, when you have M going this way, jumping this way, down, right? Jumping down. Look at your note. Right? Okay, so jumping down 35. Right? So you will be here. So jumping down 35. Okay? So when you see an arrow, movement is pointing this way, it's jumping down 35. The arrow is going this way, you're jumping up 35. Okay, jump down 35. Now, once you cross this point, what do you see? You continue accumulate this area here, right? So from this point C to point D, how much you accumulate? 5 times 7, so 35. So you jump down another 35. So here you back to 0.
Why do you jump down 70? Why do you go down?
No, I didn't go down 70.
Why do you have 70?
Oh, why I have 70? Because I'm jumping down this much. Okay, this much is this area. That's 35. I'm jumping down 35.
Oh, 105.
All right. Okay, so we're done, right? Okay, let me go quickly back to that slide showing the movement which way it's supposed to go. Okay. So I have quite a few slides before me. So, okay, here. Remember this one? Remember this? Okay, when you have a moment point this way, you jump down M0. That's why we just jump down 35 there. All right? Okay, so I think we'll have time just cover this two. Next time we'll continue, cover more examples. So for these two examples, any questions? Okay, if not, let me do a quick mention one point. Okay, you see here, whenever I draw the VM diagram, always start from the left, then go to the right, right? Okay, so I want you to always do this way. Because if you randomly go from left to right, okay, for the M diagram, it's okay. But for the V, you can easily get a mistake. Because the V, on this side, the positive defined differently, right? It's just opposite. So you keep one way to it, and most people will go from left. So I want you, every time you do a homework problem, start from the left, and then go to the right. Unless sometimes you couldn't figure out, you couldn't move, right? Stuck somewhere, sure. And then you can kind of get some help, think from the right. But remember, when you start from the right, the V, okay, when you start from the right, when you have a V going up, that's negative, right? V go down, it's positive. Okay, so you need to remember the sign convention, all right? Okay, any other questions? Oh. No.
So, Professor, you're saying that just hypothetically, you cut it right at the point of the moment.
You cut?
You deal a dotted line so we can examine that specific moment.
Yeah, the reason I draw a line is to point the position. So say, for example, for this one, where this peak point is, where I'm jumping at this point where the moment is applying.
What I'm asking is, how do I make that bar look like those other diagrams?
Make which bar?
How do I make that particular part of the bar look like the other diagram that shows the moments?
I'm not sure what you're asking.
Well, the other diagram.
You talk about the top graph or the middle or the bottom?
No, just that moment area.
The moment, the last one, the moment diagram?
No, the actual bar itself.
Okay, the actual bar, yeah.
How do I make it look like those other, the other slide that you showed? How do I cut into that segment, cross section, and make it look?
We don't need any cut. You're not.
Which direction do I examine?
Okay, we're now talking about like a 2D picture, right? So you can have force that's going upward or downward. That's one. And then you're going to have movement. The movement will be either this way or the other way, right? So it'll be this way, clockwise or counterclockwise. So only there are two directions. So we talk about now a 2D picture, right? We're not talking about movement along this way. That's the torsion. We already covered it, so we're not talking about that. So the movement will be either this way, bending clockwise, or this way, bending counterclockwise. So that's only two possible directions we're talking about. All right.